if you have some matrix A, which is equal to this, you know what? I could give it to you in terms of A11, A12, A13 like I did before. But let me just give you a numerical example straight off. And actually, let's take the matrix we were discussing before, this simple matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, if we want to calculate the determinant of A using this LaPlace method, you can expand across any row or down any column. Let's first illustrate it by expanding across the first row. Let's expand across the first row. And I'll just give you a simple method right now. Later on, we'll consider a slightly more complex and rigorous derivation. If you're expanding across the first row, what you do is the following. You take this element, 1, that's first column, first row, the first element in the first row. You take that, and then you multiply it by a determinant that's formed by deleting the first row and the first column. We're dealing with this element here. So actually, this is called as the minor of this element. The minor of this element right here is simply the determinant that's found if you delete the row and the column corresponding to this element. So the minor of this element would just be this. It would be 5, 6, 8, 9. Okay, that's the minor associated with that number 1. Okay. Now we go to the next element. However, when we go to this next element, we have to change its sign. We didn't change the sign on the first element. But on the next one, we will have to change its sign. So instead of this becoming a 2, it's a minus 2. And then you multiply that minus 2 by the minor of that element. And now, for this element right here, its minor is found by deleting the first row and the second column. So what you're left with is this, 4, 6, 7, 9. Next, we take the last element in that first row, which is the 3. We do not change the sign of that element. See, the pattern is for the first element in the first row, we leave the sign unchanged. The next one, we change it. The next one, we leave unchanged. You alternate. That's the pattern if you're going across the first row. So we have a plus 3. The minor of this element 3 is just this, 4, 5, 7, 8. And now we have to calculate these 2 by 2 determinants and multiply them by their coefficients. Okay, so we have 1 times, when we evaluate this determinant, it's 45 minus 48. Okay. Minus 2 times the value of this determinant is going to be 4 times 9 is 36. Minus 42. Plus 3 times 4 eighths are 32. Minus 35. All right, now let's calculate these sums. And what do we get? We get 1 times a minus 3 minus 2 times minus 6 plus 3 times minus 3. Or we get minus 3 plus 12 minus 9 equals 0. This makes sense, doesn't it? Because we'd already seen that these 3 column vectors of this matrix are linearly dependent. Actually, the quick way is not to try to find values for K1, K2, K3 that make that statement for linear dependence true. The quick way is just to calculate the determinant. If you find the determinant is 0, then that guarantees that the column vectors are linearly dependent. If you find, on the other hand, that the determinant is not 0, then they're linearly independent. So this then is the determinant test for linear dependence and linear independence. Okay. And the reason why we're interested in this is because if the column vectors or row vectors in the coefficient matrix are linearly dependent, you will not get a unique solution to the equation system. On the other hand, if the column vectors are linearly independent, then you will get a unique solution to the equation system. If the determinant of A equals 0, then matrix A is said to be singular. On the other hand, if the determinant of A is not 0, then A is, what would you guess? That A is, in this case, non-singular. Okay. Okay. We will come back to this shortly.